All right, so we've gotten our introduction to waves out of the way. Now we can get into some of the specifics. Again, this entire unit's on kind of that periodic motion, that wave type motion, and what I really like to think about is it's about music and pictures, okay? And so we're back to the music portion of it, okay, or sound waves. So this is our kind of discussion on sound waves, and I think it'll fit in 15 minutes. I'm not sure. It might go over because there's kind of a lot of topics, and I'll probably go on for a little bit. All right, so where are we at with sound waves? First of all, sound is a longitudinal wave. It's one of these mechanical waves. It needs to have a medium in order to travel, okay? Sound cannot travel through a vacuum. That'll be probably one of the demonstrations I'm going to try to pull out and show you that you can't transfer sound through a vacuum. So in other words, it has to have matter to move, okay? So like air molecules, and that's typically what we see here. And in my little picture, you can see that we've got our speaker, and our speaker starts to take the air molecules that are around us and groups them into these compressions and these rarefactions, okay? So those were the two parts of longitudinal waves. So we see our compressions and our rarefactions, similar to crests and troughs. Then what happens is our ears perceive this changing of air pressures, okay, and it pushes on the inside of our ear, and inside there we have our eardrum, okay, which is a membrane that vibrates back and forth, and so that forces us to have our nerve endings perceive those sounds, okay. So it's about moving air molecules, and that's kind of the big thing is that you move that air molecule and then it's out there, and then the energy dissipates as it goes through, okay. So now, when we as humans are listening for sounds, we have kind of this audible range, okay? It's a range of frequencies that we're able to perceive. Not everybody can hear these though, okay? It's a range that is set for most humans, but again, it depends upon you as an individual. So like, I can't hear at certain frequencies where other people can. This audible range generally goes between 20 hertz to 20,000 hertz, okay? So in other words, a really low frequency to a very high frequency. If you're into looking at speakers, a lot of your subwoofers, you'll actually get them and you can buy them based on the frequency that they'll produce. And they'll produce frequencies lower than 20 hertz, and we'll kind of get into why on earth would you ever want a speaker that produces something that's outside of that audible range. Other animals can hear at different ranges, like a dog can hear at a higher frequency than humans can, so they actually perceive something outside of our audible range. These give us the ultrasonic and our infrasonic, okay, so there are these ranges of sound waves that can happen outside of what we consider to be audible, okay. We use ultrasounds all the time when we're trying to take images of things, and so it's kind of like a sonar type deal where we're bouncing waves off of things and getting an optical density. Okay. When we as humans listen to sounds, we describe it as the difference of a pitch that it may have. Pitch relates directly back to a frequency. So you'll have a frequency that's being played, and then that's a perceived pitch. Okay, pitch is kind of a human thing. It's a relative to what we can hear, but it's related directly back to that frequency. If we are playing the piano, we might play the middle C on the piano, and that middle C has a set frequency. Okay, so there's an actual frequency that's associated with that. But then we kind of adjust our pitch off of that. So if I'm in choir, I kind of adjust to make sure that I'm in tune with that pitch, okay? And so that's where we start to look at that. Sound itself travels at kind of a speed. So like any wave, waves all will propagate at a certain speed, okay, because speed of a wave is the wavelength times the frequency. And sound is nothing different than that. It wants to travel at a speed. Now, the speed of sound is dependent upon the temperature, okay? So the speed of sound at 0 degrees Celsius is 331 meters per second. It increases though as we change that temperature, okay? So in other words, temperature changes the medium then allows us to transfer the wave at a different rate, okay? And the change in temperature is a 0.6 meters per second per degree Celsius. So if we look at this and we say it's 25 degrees Celsius out, we would take 25 times 0.6, okay, so 25 times 0.6 would give us a 15 meter per second increase to the speed of sound. We'd add that together to the 331, and that would give us like a 346, okay? So the speed of sound at 25 degrees Celsius is 346, where at 0 degrees Celsius it's 331, okay? Now again, we talk about sound and how sound is generated, and sound actually propagates in kind of a spherical manner, okay? You can think of it like a balloon as it's being blown up. So it starts out kind of small and that sphere expands as it goes. And so sound is the same thing. The wave of a sound actually propagates in that kind of spherical sense. That gives us some different things to look at when we start to consider how do we perceive sound and how is that sound hitting us, because we have to think in terms of it's a big ball of sound that's expanding out as it goes out. One of the things that's caused because of this big expansion of sound in a spherical sense is this whole concept of the Doppler effect, okay? And maybe you've heard about the Doppler effect or you've experienced it. I know everybody's experienced it. The Doppler effect is one of those ones that if you're watching like a race car or a NASCAR race and you hear the sound and you go, okay, so those are all examples of the Doppler effect. Okay, it's that change in that pitch or that frequency as the sound is traveling towards us or as we are traveling towards the sound. Okay, so there's kind of two case situations. And I'm going to describe both of those case situations, and I have a little formula here to kind of talk about this. Okay, case number one. Here we have a car, and maybe this car has the horn, and its horn is giving off a frequency of 256 hertz. Okay, so we have a sound from that horn of 256 hertz. And then what we want to do is we are right here, and we decide that we're going to go running past this car. Now, as we are going at the car, what we're doing is that wave that's coming at us, we actually experience that wave pattern quicker. It's like this. If you're on the lake and there's a nice little waves coming on the lake, and then all of a sudden you're taking your boat directly at the waves, you hear the tum 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 tum. You actually experience the waves quicker, okay, which changes the frequency of the waves. Okay, so now in my case number one, the source, I'll label the source as that, is stationary. So we have a stationary source. What that means is that essentially this part of my equation is no longer used, okay? The V here in this equation represents the original frequency of the sound. And the V here represents the velocity of my listener, okay? So my listener is traveling at it, which means that I should get a frequency that's going to go higher. So frequency here should be higher as we travel towards the object. When we get on this side, where we're then running away from the car, we should hear a perceived frequency lower, because now all of a sudden we're going with the waves. So back to my little boat analogy, now all of a sudden you're boating with the waves, and so it's a lot less. So it's like doom, 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 because you're kind of going with it, so the waves actually kind of catch up. Okay, so here, perceived frequency is higher because we're traveling at it. Perceived frequency is lower because we're going away from it. Okay, and then this is our original frequency. Excuse me. There we go. And the V is speed of sound. V, speed of I'm sorry about that. Okay, so original frequency, V is the speed of sound in the air for that temperature, and then we have our speeds relative to the source or to the listener. Okay, so now what happens when we get to a situation where the source is moving? So now we as the listener are not going to be moving. We as the listener are going to be stationary. Well, again, that source is moving, which means that the grouping of the waves is getting scrunched together. Okay, so the frequency is going to be changing. So over here we see that we have a higher frequency, and over here we have a lower frequency. Okay, and it's all dependent upon the motion of the waves, or motion of the vehicle or the source. And so that's kind of how we use the Doppler effect. So again, we look at it in terms of the listener and the source. Okay, so now in this one, the listener is stationary, so they have a 0. Okay, and the source is positive, so again, we're going, we have to determine which one's the positive, which one's the negative. So we'll say this is a positive direction, so we would see an increase in our speed. Okay, Doppler effect, we'll see a couple of problems on the problem set on that, and so I just wanted to make sure we touched base with that. All right, sound intensity. This might be my last little discussion point here before I have to break and go into a second video by watching. Sound intensity is, again, based on that spherical increase. If you're really close to the speaker, you get more intense sound than if you're further away from it. Okay, so again, you're related back to the radius of our sphere. Okay, so again, as we increase that sphere, it's going to change the intensity of the sound that we're going to hear. Okay, and so the further you get away, the less it's going to get. It's the inverse square rule. And sound intensity is related back to this power or this energy flow. Okay, power, if you remember from when we were doing power, it was the work divided by the time, so it was energy per unit time. It's measured in watts. Okay, so it's the rate of energy flow through a given area. Now, when we start to describe sound intensity, we typically start to describe sound intensity based upon in terms of what we like to hear, which is decibels. Okay, so in other words, us talking is a very low decibel range versus, say, when you're listening to your music, you're up in this range. And if you're in jet planes and you're on the tarmac, you know, you're in this whole range here, which means you have to wear ear gear. We kind of have a threshold of hearing, okay, and this threshold of hearing is kind of the lowest intensity of a sound that we can perceive, okay, as humans. And so when we look at our threshold of hearing, it's 1 times 10 to the negative 12 watts per meter squared, okay? So you'll see this in the type of units that we like to use, watts per meter squared. This is our lowest. We also have a threshold of pain, which is like 1 times 10 to the, it's 1 times 10 to the 0, okay, is watts per meter squared. So we have a very high number when it comes to threshold of pain. We typically take sounds and we make them relative to one another, and so we always relate everything back to this threshold of hearing. Okay, that's our basis that we like to measure everything. We call this our initial or our basic intensity. And then what we do is we figure out our decibels. Decibels are a logarithmic function of what we're seeing here. And so we do have an equation that relates decibels, and so this is my decibel intensity, my relative intensity is 10 log, this is now my power of my source divided by the power of threshold. We can also look at this as I of my source versus threshold of hearing. So this would be another way to look at it as well.